Okay, yesterday we were working on the POGL for gas laws, and we started to describe pressures and factors that affect the pressure of a substance in specific states and reactions. We also began to measure and calculate the value of pressure in specific scenarios. So today we are going to begin to look at some different areas relating to pressure. We're going to begin to look at some specific gas laws. Boyles' law, which is a relationship between volume and pressure. Charles's law, which is a relationship between volume and temperature. And Lussac, which is a specific relationship between pressure and temperature. Lastly, we will look at the combined gas law, which incorporates all three of these laws together in a relationship that looks at not only volume, but not necessarily a relationship between volume and temperature, or pressure and temperature, or pressure and volume, but it does all three at the same time. So it's the relationship between volume, temperature, and pressure. So real quick, wanted to go over the question with you. The opening question says, how will a change in energy of the molecules in a gas be measured? So what I want us to think about, anytime energy is changing for a gas, we can think about it in terms of temperature. As energy increases, temperature increases. As energy decreases, temperature decreases. So let's just kind of move along in our slideshow, and we will talk about each of these gas laws independently and work some problems independently. Alright, so looking at gas laws and in general for our measurements that we will be taking and calculations that we'll be doing, it's important to know what units of measure we're going to be using. So for volume, which is typically represented by V, we are primarily going to be using liters for our unit of measure. However, sometimes it will be in milliliters in our problems and such. The only thing we need to remember for Charles, Boyle, and for Charles's law, Boyle's law, and Lussac, it's okay to use either milliliters or liters. However, when we deal with the ideal gas law, we need to pay attention that units should be in liters. And that has to do with what particular R constant that we're going to use. Pay attention to make sure that it's in liters or milliliters or whatever. That will change a factor. So please pay attention to that. Temperature, always convert to Kelvin. Now, most of the time our temperature will be given in Celsius, so Kelvin equals degrees Celsius plus 273. And that's just an important factor to remember. And for the most part, in this unit, I will give you pressure in terms of atmospheres, but kilopascals are also acceptable in this. Now today, on some of the problems that we'll work, we'll see units of measure in millimeters Hg or torr, which essentially those two are the same thing. 1 atmosphere is equivalent to 760 millimeters of mercury. That measurement typically comes from a barometer, and so it's just kind of important to know that conversion. So if I said that we had 748 mmHg or 748 torr, if I wanted to know that in atmospheres, we would simply just do our dimensional analysis. We're wanting to convert to atmospheres, so we would essentially go 1 atmosphere is equivalent to 760, and then we do the calculation. 748 divided by 760 gives us that we would have essentially 0.948, sorry, that gives us 0.984 AT. Alright, just be aware of those units as we're doing our calculations. Alright, so as far as Boyle's law, what we need to pay attention to in Boyle's law, we are only manipulating the volume and the pressure in Boyle's law. So this is an inverse or indirect relationship. Inverse relationship. So in this, as one variable increases, the other variable will decrease. So if we increase volume, pressure will decrease. So any problems that we do with this, if when we look at our initial pressure and our initial volume, let's just say that we were solving for a new pressure. So if we increase pressure, that means, well, if there's an increase in pressure from our initial pressure to our new pressure, then that means our volume should decrease. So if we look at it in relationship to this graph, we can see as volume increases, pressure decreases. So we are going to look at it in relationship with this equation. Initial pressure times initial volume is equivalent to the new pressure times the new volume. So let's look at this mathematically. So if we look at the homework sheet, let's do problem 1 together. One of the things that I want us to be very diligent in doing as we're working on these type of problems is keep track of our givens and our unknowns. This will help us out as we do more and more or increasingly complicated problems. So our problem here is a sample of oxygen gas occupies a volume of 250 milliliters at 740 torr pressure. What volume will it occupy at 800 torr? So we immediately should notice that we have a change in pressure. Now, in this problem, since both of our pressures are in the same unit of torr, we don't have to make any kind of conversion or anything like that. The other thing to notice is that our volume is in milliliters. So I'm just going to take some notes over here on the side that I have my P1, my P2, my V1, and my V2. These are the things that I need to keep track of and see what they are and where they are in the problems. So I have a V1 of 250 mils. I have a P1 that is 740 torr. I have a P2 of 800, torr. Not real sure what happened to my handwriting right there, but it just kind of went weird. And then my unknown, we want to know what volume. Now, a couple of things that we can notice right away. One, our initial volume is recorded in milliliters, so we should expect our new volume to be in milliliters as well. And then if we remember that this is a direct relationship, we should also notice that our pressure from pressure 1 to pressure 2 increases, so we should be seeing a decrease in volume in this case. And that's just going to be something to look for mathematically at the end. So let's go ahead and plug our numbers into our equation. So looking at it, and we're just going to fill it in, our P1 is 740 torr times our V1, which is 250 milliliters, which is equivalent to our new pressure of 800 torr times V2, which is our unknown, which is what we're solving for. Now let's just do some algebra here real quick so that we can isolate our variable of V2 on the same side. If we divide both sides by 800 torr, that will cancel 800 out on this side and move it to the side with our numbers. So essentially we have 740 torr times 250 milliliters divided by 800 torr. Couple of things couple of housekeeping tips. Just to kind of prove that our units are going to be in milliliters, we have torr divided by torr, so that cancels, leaving only milliliters as our units. So we can see that there. So let's take a moment and solve our equation. Now, as we do the math, what we should come up with is a number like 231.25. But remember, we need to pay attention to significant figures. So as I look through my problem and my givens, each of my given, I have 3 sig figs. Notice the decimal, that's telling us that we have 3 sig figs in each of these, so I can only report my answer in 3 sig figs. So that means my answer is 231. Let me make sure that's clear. So 231 should help us, should be our answer. Alright, moving on to Charles' law. Now, Charles' law is a relationship between temperature and volume. So when we're looking at temperature and volume, we need to understand the relationship that happens there. This is this one is a direct relationship. Let me back up and correct a statement real quick. This is not direct, this is inverse. So, sorry about that. That was a mistake on my part. It is inverse, so as one goes up, the other one will go down, and vice versa. I did say that correctly, I just used the wrong word. It's supposed to be inverse, not direct. Let me just double check. Yes, I said inverse here as well. Had I been in the classroom, my students would have corrected me really quickly. Alright, so going back to this one, this is a direct relationship. So as one side increases, so if we increase volume, that means that temperature should show an increase as well. Looking at the equation relationship here, we have V1 over T1 is equivalent to V2 over T2. So if we just put some numbers to this, let's just say that we have a volume of 1 milliliter and a temperature of 2 Kelvin. So let's say that we increase the volume by a factor of 4. So we go from 1 milliliter to 4 milliliters. What would our new temperature be? Well, if we increase this by a factor of 4, that means that our temperature increases by a factor of 4 as well. So our new temperature would be 8 Kelvin. So if we look at this, 1 over 2 is equivalent to 4 over 8. Both of them gives us a factor of 0.5. So that's kind of what we're doing there as we manipulate this. So let's work an equation together on the practice work, the homework, and see how this works. Alright, so doing a practice problem with this, we have this relationship V1 over T1 is equal to V2 or over T2, or we can write it as V1 times T2 is equal to V2 times T1. So when we're doing these problems, we need to keep track of the following variables: V1, V2, T1, and T2. So let's look at number 1 again. A sample of nitrogen occupies a volume of 250 milliliters at 25 degrees Celsius. What volume will it occupy? Alright, so first thing that I need to remind us is that anytime we are dealing with temperature, we are going to convert to Kelvin. So a couple of quick things right here. Our temperature is in Celsius right now, so that's going to be 25 plus 273, which will give us a new temperature, or a converted temperature, of 298 Kelvin, and 95 plus 273 gives us a temperature of 303 Kelvin. So let's go ahead and fill that in our given notes over here. T2 is 303. T1 is 298. Our initial volume is 250 milliliters, leaving our final volume as our unknown. Now, just some relationship notes, or some unit notes. If our initial volume is in milliliters, we would expect our new volume to be in milliliters. Excuse me. Alright, so let's go ahead, plug this in. I am actually going to use this format, plugging it in. It just makes some manipulation of the equation easier. So let's go ahead and fill in our numbers. So V1 is 250 milliliters times, notice that's T2, so 303, equals V2, which is our unknown, times T1, 298K. Now, again, just some manipulation. I want to have V2 by itself, so I'm going to divide 298 on both sides, so it'll cancel on the right and move to this position on the left. The only reason why I do this is just to show you our unit cancellation. Kelvin cancels, leaving milliliters as our new unit. And then we can go ahead and solve. Now, it really doesn't matter the order that you do this in. I just like to go ahead and multiply my numerator before I divide by my denominator. That just is some house cleaning stuff for myself. So go ahead, take a moment, pause the video, solve, and we will come back. Alright, so when we do this, when we calculate the answer, hopefully you paused it and you're not just waiting for me to give you the answer. The answer that you come up mathematically is 254.1946. So we need to go back and look what are our significant figures in this problem. So we have 250 milliliters, so that's essentially 2 sig figs here, 2 sig figs for each of our temperatures. So we're going to report our answer in 2 sig figs. So again, 254. So our answer would be 250 mils. You could, as far as me grading this, I probably wouldn't have taken off if you did 200 and I wouldn't have taken off if you did 254. Actually, we are going to report it as 254. Simply because that's the only way that we're going to see the change. Let me double check my math real quick, make sure everything is coming out. Yes, we are going to report it as 254 milliliters in 3 sig figs, just because this one, if we don't, we're not going to see a change. A couple other things to pay attention in this. So going back to our relationship, we said that this was a direct relationship. So what that means is if our temperature increased, we should also see an increase in volume. So we saw a temperature increase from 298 K to 303 K. So we should also see an increase in the volume. So we go from 250 mils to our new one of 254 mils. Now, Lussac is going to be very similar in the working of the problems as it was to Charles's law, in that we have a direct relationship. The only difference is in Charles's law, we're comparing volume and temperature, and in Lussac, we're comparing pressure and temperature. So let's go ahead and see what's happening here. This is the equation that we'd be using, and like Charles's law, the graph, when we look at pressure versus temperature, we would see a linear graph, and it's going to go up at a fixed slope. And so the same thing, just looking at this numerically, if our initial pressure was 1 and our initial temperature was 2, and let's just say that we went up by a factor of 3 this time, so our new pressure is 3, that would mean our new volume should be 6. Again, this is a direct relationship, and it's dealing with pressure versus temperature. So we're going to go ahead and work a problem like this. On the practice sheet, I gave you the equation as P1 over T1 equals P2 over T2. I'm just going to do a little bit of manipulation here that gives me P1 times T2 is equal to P2 times T1. Sometimes it's a little easier to manipulate the equation there. So that just means that we need to keep track of P1, P2, T1, and T2 when we're doing these equations. So a sample of gas in a closed container at a temperature of 100 degrees Celsius which is 373 K, and 3 atmospheres is heated to 300 degrees Celsius, which is 573 K. What is the pressure of the gas at the higher temperature? So let's go ahead, keep track of our givens. So temperature 1 is 373 Kelvin. Our new temperature is 573 Kelvin. Our initial pressure is 3 atmospheres. So we want to know our new pressure, and since our initial pressure is in atmospheres, we should deduce that our new pressure is going to be in atmospheres. So let's set up our equation. Again, I didn't really say this. I'm hoping it's understood by now. Always convert to Kelvin from Celsius. The other thing to pay attention, this is a direct relationship. So we are looking at our temperatures. We see an increase in temperature. So what should we expect to happen to our pressure? We should also see an increase in pressure. So setting up our equation, P1, we have 3 atmospheres times T2, 573 Kelvin, is equal to P2, which is our unknown, times T1, which is 373 K. Now divide both sides by 373. That gets rid of 373 on this side, leaving only P2. I'm going to draw a box for my answer just to help my teacher out a little bit when he's grading this, just so he has a nice clean place to see the answer. So we take, we're going to take 3 atmospheres times 573 K, divide it by 373, and that will give us our new answer. Our new pressure. So go ahead, pause the video and take a minute to solve. Mathematically, you come up with an answer like 4.6085, and when we look back at our problem, we see 4 sig figs here, 2 sig figs here, 4 sig figs here. So we should probably report our answer in 2 sig figs. So 4.608 should be reported as 4.6 milliliters. Not milliliters. It's going to be atmospheres because Kelvin cancels, and that gives us atmospheres. So that was a boneheaded mistake. Here I am telling you to pay attention to units. and I wasn't paying attention to the units. Alright, so pressure P2 equals 4.6 atmospheres. This is just some mnemonic devices to help you remember this. So for Boyles' law, temperature is constant, so we can remember BLT, if you like a BLT sandwich. Charles' law, we have Charles' law is pressure is constant, so we remember the CNP and it's cheese pizza. Or Lussac is volume is constant, so we can remember the G, L, and the V, and we eat our green leafy veggies. Alright, last one. Combined gas laws. This is where we put all three of the previous gas laws together and we can manipulate them. So I would recommend remembering this equation, this setup, because any of the previous three types you can use this equation to solve it. Whether it's Boyles, Charles, or Lussac, you can use combined law to solve for it. So don't worry about this note for table T. That was something for Chem 2 last year, and I just haven't edited that yet. But please make a note that you must always convert to Kelvin. The most mistakes I find when students do the homework and when they do the test is they do not convert. Please make sure you convert. Alright, so I just told you that you can use this one for any of the three previous ones, and let me show you why. Because if we are dealing with a Boyles law question, temperature is constant. So we should see that we have P1 times V1 equals P2 times V2, which Boyles is initial pressure times initial volume is equal to new pressure times new volume. Alright, so let's manipulate the equation. Let's manipulate it again a little bit. And let's say that we are holding volume constant now. And all of a sudden we see that we have Lussac. Pressure 1 over temperature 1 is equal to pressure 2 over temperature 2. Or if it is a Charles's law problem, we see that pressure is constant and we have V1 over T1 and V2 over T2. Alright, so let's go ahead and look at one of these problems. And this is actually going to be a problem that asks us to use combined gas law. So we're going to have factors of pressure, volume, and temperature being manipulated in this. Again, convert to Kelvin. Make sure you do that. So let me go ahead and write you out the modified equation. And again, I just like doing it like that because I sometimes make boneheaded mistakes in manipulation, so this helps me to not end up with 1 over T2 or something like that and then have to really tax my brain, and I just like to keep things simple. Alright, so in this we're going to need to keep track of P1, V1, T1, P2, V2, and T2. So we have more to keep track of in this problem. That's why I've been stressing to somewhere keep track of your givens from the problem, and that makes it easier for us to know what to solve for. A sample of nitrogen monoxide has a volume of 3.0 liters at a temperature of 20 degrees Celsius and a pressure of 1.5 atmospheres. What volume will the sample occupy at 30 degrees Celsius and 2.5 atmospheres? So just going through here real quick, we have a V1, T1, P1, this is V2, this is T2, and this is P2. So let's go ahead and write it over here. So pressure 1 is 1.5 atm. V1 is 3.0 liters. And temperature 1 is 20 degrees. So 273 plus 20 will give us 293 Kelvin. Alright. Looking at pressure 2, we have 2.5 atm. Our volume 2 is our unknown, and our temperature 2 is 30 degrees, so that's going to mean that we have 303 Kelvin. If you don't know how I got these numbers, I simply added 30 plus 273, giving me 303, and 20 plus 273, giving me 293. Alright, I'm going to go ahead and erase this so I have some room to work, and then we will set up our problem. One of the things that I always like to be is I like to be nice to my teacher, so I give them a little answer box there. Make it easy for my teacher, him or her, to look over there and see what your final answer is. So let's go ahead, plug this into the equation. So pressure 1, 1.5 atm times volume 1, 3.0 liters, times my T2, 303 Kelvin, is equal to 2.5 atm times V2 times T1 is 298K. Now, I can divide both of these on both sides. Now, up until this point, it really hasn't mattered the order that we put them in the calculator, or the order that we do this, but we need to make sure that we take all of these together and these together before we do our division. Sometimes if you don't do that, if you do it a little bit out of order, you're going to come up with some wrong numbers there. So just make sure you take care of that before you do it. Let me go ahead and show you what units we're going to end up with. So Kelvin cancels Kelvin, atmosphere cancels atmosphere, leaving us with liters as our final answer. So pause the video and take a moment to do this calculation and see if your answer matches my answer. Alright. So doing the calculation, I got a number like 1.8302. Looking back at my problem, 2 sig figs, 2 sig figs, 2 sig figs, 2 sig figs, 2 sig figs. So I'm going to report my answer in 2 sig figs. So when I look at this, I will report it as 1.8 liters. Now, so we can go ahead and do this. Look at the inverse and direct relationships and see which one caused the bigger change. Not so much worried about that, but I am worried about you setting the problem up correctly and coming up with the right units for your answer. So that concludes our lesson for today. Tomorrow we will begin looking at Avogadro's law and the ideal gas equation. So thank you for your time.